Hello, mentors, and welcome to Art Symmetry. So this is activity 3 of Create and Transform, part 1 from our meeting. Let's take a look at what this is about. So we'll analyze each symmetry for several shapes. We'll classify the shapes in categories according to the symmetries. And finally, we'll discover that exactly having two symmetries is impossible. So which symmetries are we talking about? Well, in the previous activity, we explained that to students without mentioning those symmetry explicitly, but now they know, and it's easy now to make the connection. So the first, it's left-right symmetry flip. So a reflection along the vertical axis. The second, it's horizontal axis symmetry, so up-down symmetry when you reflect or when you flip. And the last symmetry, it's rotating half a turn, so 180 degrees. Those are the three symmetries that we're considering. So what's going to happen is we'll have a bunch of cards of these 8 shapes, and they're going to try to discover what's the symmetry. So they're going to pick one shape card from 1 to 8, each team of 2 students or so. And then what they're going to do, individually, then they team after. So individually, they pick one of these cards. And what they're going to do is they're going to draw it here, the original, and they're going to do all possible moves. So flipping left to right, flipping up to down, or rotating half a turn. And they'll see if each of these 3 ends up being exactly the same as A, why or why not, right? What fails, if not specifically. So that helps them check which symmetries the particular shape have. Later, they do team up. So they team up in, teams of 2 or so, and just discuss the result, check why they work or they don't work. Let me tell you also that they also work with these extra cards. These are good because they discuss what could happen with other shapes. So these are the questions to focus students. Which particular elements help you decide which symmetry would appear? So here we have them focus on particular elements, so triangles or lines or arrow-like shapes. For example, here you can have like an arrow going up. So that tells me that you won't have this horizontal symmetry because then the arrow goes down. So things like that. Also, which shapes were alike and how were they alike? Which categories could we make to classify the shapes? And you could follow up if you need. How about disjoint categories that have no shapes in common? Are there categories with no shapes? Can you think of new shapes that belong to them? And you challenge them specifically. Look for shapes with exactly one symmetry and go back to the drawings. What do you notice? And finally, what about the shapes with 0 symmetries? So let's take a look at the examples and the solutions, and then look at the discussion that could take place. So the shapes 1 or 2, they don't change at all. They have all 3 symmetries, and all the drawings are the same. So these are sort of the less exciting shapes because nothing is changing. 3, the flip left, right doesn't change, right? Doesn't make the shape change, but up, down, or rotating have the change. Here, you only change when you flip up or down, but when you rotate or flip left, right, it will change. Here, something similar happens. Left, right is the same, but these 2 symmetries you change. For this one, this is pretty cool. It changes when you flip it up or down or left to right. But if you rotate it half a turn, notice that this is like number 2 or so, or like an S, but backwards, it will stay the same. So it has this rotation symmetry. This is the more tricky one because you would think that it doesn't change at all, but these lines, these vertical lines here, diagonal lines here, will actually make it change when you flip it, when you mirror it, either vertically or horizontally. But when you rotate it, the diagonal line, still a diagonal line. So that's the main observation here. Here you just have this flip. It's like an arrow, like pointing right. So if you flip it along the horizontal axis, it's still pointing to the right somehow, but it changes in these two rotations. And the final shape, this is just extra one, just to illustrate what a student could create or use for another shape. This is what happens. So we have this as a summary table. So let's go back to the instructions. So what happens is each student passes the student workbook to the right or the team to be checked by another student or a team of students. And then after, all students will collaborate to fill out the table on page 4 of the student workbook and discuss the results. So they'll fill this table and they discuss the result. All shapes have at least one symmetry. That's the first observation they could be making. And then we challenge students to create on the other shapes that could have 0 symmetries. That's easy. You can do it. And actually, these type of shapes here kind of have the answer. But there's several examples. There's many examples, and it's very easy to come up with symmetries, just random shapes that present 0 symmetries. The next observation is that if you have one yes, then that's it. Because if you try to have 2 yes, then you jump to 3. So either you have 1 yes or 3 yes, but you cannot have 2 yes. Of course, 0 yes for other ones. What does it mean? That you cannot have exactly 2 symmetries. But maybe it's because these shapes were carefully chosen to satisfy that. So part of the activity here is students trying to come up with shapes that have a yes, yes, no, or a yes, no, yes, or a no, yes, yes. So exactly 2 yes, exactly 2 symmetries. And what ends up happening is that it's just impossible. They'll discover that. Now, in this activity, we don't care about justifying that, just because in part 2 we'll have that. So it's more discovering and stating the conjecture that it's impossible to do that. But later we'll do. Now let me illustrate how making student thinking visible is important, and what could you anticipate what they could think and say when you start asking students these important questions here to focus them. So this activity is kind of 2 parts. The first part is just do lots of, moves and fill out this table. That's done easily and fast because every team has, some shapes to do. So this could be done sort of fast, in a fast fashion. And then the second part is the discussion. So about shapes that are alike, they could say things like shapes 1 or 2 are alike. They look very balanced and all around, they all have symmetries. They could also say things like 4 and 8 are similar. 4 and 8, look at it here. And they could say they remind me of an arrow facing left or right. That's why they don't have left-right symmetry, but they have up-down symmetry. So they're still generalizing and isolating some elements that give symmetry or lack of symmetry. So it's not just saying yes or no, and this has symmetry and no, but what are the features that make it so? For example, this looks like an X. And when I was playing the game before, I found that X had all symmetries. So that's why I expect these to have all symmetries, things like that. So we're discussing shapes. For creating categories, they could start with 3 categories: the left-right symmetry, up-down flip symmetry, and half-turn symmetry. But you would tell them that these categories have elements in common, and we want just separate categories. So they should hopefully arrive at counting. So 4 categories, 0, 1, and 3 symmetries. This will be a cool way to measure how much a symmetry a shape has. So this measures the degree of symmetry. And we want students to get to this classification eventually. For the 2 category, they could say, I try many times, but I just can't produce a shape with 2 symmetries. So somehow I give up, but I'm not saying it's possible or impossible yet. I just can't right now. I want to keep trying. Wait, I can't get this. They still believe that they can. They still don't know the bad news that they cannot. I give up, help, can I get a hint? So this feels like a stages, right? When you have a bad news or something, how to cope with this should maybe feel a little similar. They still believe that it's possible, but gradually they convince themselves that it's impossible. I'm starting to think that this is impossible. I feel like when you have two flips, you somehow get the half turn. And then here just they get somehow convinced. I see that no shapes have exactly two symmetries. Don't know why, but it must be true. So now they feel it and they have an intuition. They just cannot put it to words explicitly. I tried like 10 times and it failed, so it must be impossible. So this is good enough. Of course, some advanced students or students that are really motivated, they may start to get to the proof, to the visual explanation relating the flips and the turn, and that's fine, but otherwise you'll delay to part 2. For the drawings, something really cool happened. So I discovered something interesting. For shapes with just one symmetry, 2 drawings are equal to each other, and the other 2 are also equal to each other. I don't know why, but I tested it a lot. So that's also some discovery, which is actually very, very related to the 2 category exploration. Let's take a look. For example, this shape has just one symmetry, right? And you actually get these 2 shapes to be equal, and the other 2, they're also equal. They're different from A, but they're equal to themselves. Is this a coincidence? It's not. Let's take another look here. You just have one symmetry, and the ones that were not producing a symmetry because they were not equal to A, they were equal to each other. So that's gonna tell you somehow that these 2 become equal because these didn't change A. So there's some algebra here, some combination of the moves that produce equality here. Same as here, then not same becomes same between each other just because, yeah, they were not equal to A. And because this kind of save the day and make them be equal. Another discovery your students could make is that when there's no symmetry, the 4 shapes, they're all totally different. And we don't have examples here, but they will, when they make their own examples, they will discover that. I discovered that if the 2 flips produce the same shape, then the original shape has half-turn symmetry. So all these conjectures, they're very valid, and you're hunting for them. You have the table and the drawings to work with. So these activities should lead into part 2 then, which is working with a mural. And they already know that they cannot check exactly 2 of these, hopefully. And here in part 2 is when they will try to ask the why question. Can you have exactly 2 symmetries? What happens? Why? And the hint is to relate the 3 transformations and discover that 2 of them produce the other. But again, that's part 2. So hope you enjoyed this video and the meeting on Wednesday, and have fun. See you in another video. Goodbye.